So you work for an online delivery service and you would like to implement some type of new business offering. But in order to convince the executives of the company that it will be profitable, you need to prove to them that the average orders per customer per week is greater than 4. So let's assume that it's too expensive to perform this study on the entire population, or you don't have the data for the entire population. So what you will have to do is you'll have to draw a sample from the population and then conduct a study or a test so that you can infer from the sample data what the average orders per customer per week will be for the entire population. So using the sample to infer the population mean. And what we're going to do for that is a t-test. Now, in order for a t-test to work, the sample data needs to be normally distributed. So in order to check that, I've just created a histogram based on the sample data. And as you can see, that is approximately normally distributed, so that's fine. So the process is you want to start with your hypotheses. So it's a very quick process if you just use XLStat, which is what I'll be using. But I'm going to go through sort of the basic process just to see what it looks like. But if you're using statistical software, all you'll do is go up to one sample t-test and then you input your parameters. But just a quick run through, your alternative hypothesis, basically what you want to do is you want to prove that the average is greater than 4. So your hypothesis will be, or your alternative hypothesis is that your average is greater than 4. So therefore your null hypothesis is that your average equals 4. Okay, so that's your hypothesis. Now the first thing you need to do is calculate your rejection region. Now that's where the t statistic comes in. You're using the student's t distribution. So you'll have a look at the table. If you're doing it manually, you'll have a look at the student's t distribution table and then determine based on the alpha level what the rejection region is. So in this case we'll use an alpha level of 1%, and the reason for that is because typically your alpha level will be 5% or something like that. But if you determine that the type 1 error is too large, or the cost of making a type 1 error is very costly, which in this case would be if you determine that the average is greater than 4 and you go ahead and implement the process and you end up losing a lot of money, that's quite a costly problem. So thinking that the average is greater than 4 when it actually isn't is quite costly in this case. So we'd want to minimize the chance of making that type of mistake. So that in this case would be a type 1 error. So the reason we make alpha 1% is so that we can have a greater degree of confidence. If we conclude that the average is greater than 4, we've got a greater degree of confidence that this is actually the case. So basically if the type 1 error is very costly, then you'll have a smaller alpha, which in this case is 1%. So then you'd use the alpha and the degrees of freedom to determine what the rejection region will be, and then you'll use the mean and the standard deviation of the sample distribution to calculate the t statistic or the test statistic, and then you'll compare the test statistic to the rejection region, and also look at the p-value to determine whether or not you can reject the null hypothesis in favor of the alternative. In a case like this, you might actually know the size of the entire population. So if you know that you've got 25,000 customers that use your service, then you would be able to use something called the finite population correction factor. And I've got, first let me show this perhaps. So this is the test statistic. Let's just focus on the top part. So that's your sample mean minus your hypothesized mean, and so your, as we can see, the hypothesized mean, we hypothesize that the mean is 4. So that will be where your test statistic comes from. So that's the difference between the sample mean and the hypothesized mean divided by, and this is called the standard error. And what happens is that if you know the size of the population, you can use the finite population correction factor in order to correct for the finite size of the population. Because if you're doing a t-test, then the standard error is good if you've got an infinite population. So if you're inferring the mean for the weight of all adult males, then you've got an near infinite population. Or the flip of a coin is a good example of an infinite population, because you can flip the coin as many times as you want. However, if you know the size of the population, in other words the population is finite, then you can use the finite population correction factor in order to adjust for that. So the standard error then, or the standard error is then this. Instead of just standard deviation divided by the square root of the sample size, the standard error, if you take into account the finite population, is the standard deviation divided by the square root of the sample size multiplied by the square root of the population size minus the sample size over the population size minus 1. So, having said that, I don't want to make this video too long. Let's say 12 minutes. Okay, so now that we know that, we can actually calculate the t-statistic by ourselves. Let's just quickly calculate the average and the standard deviation. That's the average, and you must make sure you select standard deviation for a sample. Where are we? Okay, so now I've got our average and our standard deviation. If we calculate the t-statistic, that will be our average minus our hypothesized mean, which is 4, and we'll divide that by the standard deviation divided by the square root of the sample size, which is, I think it's 247, or we can actually just say count, just so we don't make any mistakes. Good. So square root. So you've got the difference between sample mean and hypothesized mean divided by, let's put this in brackets so there's no mistakes with the order of operations, divided by the standard deviation over the square root of the. So there we've got our test statistic, which is 8.52. And perhaps we might even want to take this and correct it for the finite population. So let's just say that our finite population population size, let's say that's 25,000, then our t-statistic there for the finite population. So now we've got our difference divided by the standard error, which in this case would be the finite population correction factor. So the standard error would be the standard deviation divided by the square root. So that's correct. So we take that and we multiply that by the square root of the population size minus the sample size, which we know is 247, square root of that divided by the population size minus 1. Okay, so now I've got the difference between sample and hypothesized means divided by standard error, which is the normal standard error multiplied so this is the normal standard error multiplied by the square root of the population minus the sample size, and then the population minus 1. Good. So that should give us the t statistic, or the test statistic, taking into account the finite population. So that's what you could do for a situation like this. However, I'll be using XLStat, so I think that will be using the normal test statistic. But it's just good to know that if you're dealing with a situation where you've got a finite population, then you've got that option as well. Okay, so let's look at what XLStat looks like. So we've got the parametric test, which is a one sample t-test. Just for interest's sake, the z-test would be used if you actually knew the standard deviation of the population. Of course, that's hardly ever the case. So we'd usually use the t-test in this case. Okay, so we've got our data. Let's just check that that's correct. Got down to 250, one sample, students t-test, and then our hypothesis, or alternative hypothesis, is that our mean is greater than 4. Here it mean 4, significance level of 1, which in percentage points. Okay, confirm that 247, it's our sample size, and that gives us, and here we can see the test statistic, which is 8.52, which is what we calculated over here, 8.52, and that's our rejection region. So our test statistic exceeds our rejection region, and our p-value is very small, so we can thus reject the null hypothesis in favor of the alternative hypothesis, which means that we can say, or we can conclude, that the average amount of orders per customer per week is greater than 4. In other words, we can go ahead and implement whatever business offering we've been working on. Just one thing that I forgot to mention is that the rejection region determines or depends on the type of test. So if your hypothesis is greater than or less than the mean, then you'll be using a one-tail confidence interval estimator. However, if the alternative hypothesis is simply that the average does not equal 4, then you've got the two-tailed estimator, which basically divides the alpha by 2 and then creates the bounds on either side of the mean, if that makes sense. Yeah, so as you can see, it's a very quick test to conduct with the statistical software. I just took a bit long to sort of go through what's happening, but if you've got your data and you've determined that it's normally distributed approximately, at least, then you can go ahead and do the test, and the test will tell you what you should be able to infer from the sample data. So that's a nice way to bring some statistical evidence to your executives and tell them or prove to them that there is a good chance that your new business offering is going to be profitable.